Today we're doing a complete deep dive into Model Context Protocol or MCP. This is a standardized protocol that Anthropic announced for connecting AI systems to external data sources. We'll start with the protocol fundamentals and architectures, and then we'll examine the key components, hosts, servers, resources, and tools. After that, we'll discuss implementation patterns for production systems, including security and authentication strategies. Finally, we'll talk about integrating MCP with the existing AI workflows and real-world deployment considerations. So let's get started. So what exactly is Model Context Protocol? MCP is a standardized protocol for AI data integration. Think of it as a universal interface connecting large language models to external data sources. Anthropic announced this as an open standard, meaning this entire ecosystem can adopt it, not just Anthropic products. The key value here is eliminating custom integrations for each data source. Before MCP, if you wanted to connect your AI assistant to Slack, GitHub, your database, and various other APIs, you would need to build custom connectors for each one of them. That's a significant engineering and maintenance work. Here's a core problem MCP solves. Traditional approach is that you build custom connectors for each data source. For example, there will be a Slack connector, GitHub connector, PostgreSQL connector, and Google Drive connector. This creates an n times m problem, where n is the number of AI applications and m is the number of data sources. With MCP, any AI assistant implementing the MCP client can connect to any MCP server. Instead of n times m connections, now you have n plus m connections. If you have 3 AI applications and 10 data sources, that's 30 custom integrations in the old world, but now only 13 implementations will be there with MCP. This scales beautifully as you add more data sources or AI applications. Now, the key difference between MCP and RAG is that RAG retrieves documents, embeds them into vectors, and returns the text chunks to the large language model. It's focused on semantic search over document collections. However, MCP provides a structural access to live data, tools, and dynamic resources. MCP servers can expose databases with live records, APIs with real-time information, file systems, and event streams. While RAG is about retrieving and embedding documents, MCP is about protocol-level standardization for accessing various types of data and functionality in a structured way. They serve completely different purposes. RAG is excellent for historical knowledge and documentation, whereas MCP is excellent for live data and actions. You can combine both of them, which we'll be discussing shortly. Now let's talk about architecture. MCP has 3 core entities. First is the MCP Host. This is your AI application. Examples include Cloud Desktop, IDE extensions like VS Code extensions, or custom AI applications. The host initiates connections to MCP servers, manages lifecycle and orchestration, and handles user authentication and permissions. Think of the host as a coordinator making decisions about which servers to query based on user intent. Second is the MCP server. This is a data provider. It exposes resources, tools, and prompts via the standardized MCP protocol. Examples include a GitHub server providing access to repositories, a PostgreSQL server connecting to your database, or a Google Drive server for documents. These servers run locally or remotely and implement the MCP protocol specification. The beauty is implementation details that do not matter actually. Whether it's written in Python, JavaScript, or any other language, as long as it speaks the MCP protocol, the host can communicate with it. Third is the MCP client. This sits inside the host and handles the protocol implementation and communication. It's based on the JSON RPC for messaging, performs capability negotiation with servers, and manages the request and response lifecycle. The client is the communication layer between hosts and servers. The communication pattern uses client-server architecture based on JSON RPC 2.0. These are stateful connections that stay open and maintain state. When a server connects, it performs capability discovery. Servers doesn't declare that what they provide, like for example, which resources and tools they expose. Hosts consume these capabilities based on their needs. This architecture separates the concerns. The host focuses on orchestration and user interaction, and servers focus on providing access to specific data sources. The client is the one which is handling the protocol details. Each component has clear responsibility. Now the 3 main concepts in MCP: resources, tools, and prompts. First, resources provide only read-only data access. This includes file contents, database records, or API responses. Resources use URI-based addressing, for example, file / for file paths, or Postgres / for database tables. Resources support text and binary content types and handle pagination for large datasets. Examples include reading the GitHub issues, fetching the Slack messages, or querying database tables. Resources are passive. The language model reads from them, but it doesn't modify them. Next are tools. Tools are executable functions the language model can invoke to perform actions. Examples include creating a GitHub issue, sending an email, or updating a database record. Each tool has input schemas defined using JSON schema, so the language model knows what parameters to pass. Tools return structured results back to the language model. For example, in production systems, tools typically require explicit user approval before execution. You don't want your AI creating issues or sending emails without user knowledge. Third is the prompts. So, prompts are reusable templates with placeholders. Examples include, let's say, for example, analyze this code base for security issues or summarize recent Slack activity in the engineering channel. Prompt reduce prompt engineering burden because you define templates once and reuse them. They provide consistency across use cases and can reference resources dynamically. Here is the key distinction. Resources equal passive data. The language model reads. Tools equal active operations where the language model executes. Prompts equals workflow templates where the language model actually follows. Understanding this helps you design MCP servers effectively. Now let's talk about production implementation patterns for MCP where things actually get real. First, authentication and security. For third-party services like GitHub or Google Drive, you should use OAuth 2.0. This gives you proper token-based authentication with user consent flows. For internal systems, API keys work well, but implement the rotation policies. Aim to rotate the keys every 90 days or less. Now, the second point is the implementation of scope-based permissions. Read-only versus read-write permissions makes a big difference. If a server only needs read access for GitHub issues, please don't give it write access. This principle of least privilege actually reduces your attack surface pretty significantly. Then, its auto logging for tool execution is pretty critical. Every time the AI creates an issue or updates a record, log that with user context, timestamp, and parameters. This audit trail matters for compliance, debugging, and security investigations. You should also implement rate limiting per server and per user to prevent abuse or runaway costs. You might limit each user to, let's say, 100 requests per minute per server because rate limiting actually protects your server from abuse as well as for bugs. Now, let's talk about server deployment models. You have three main options here. Local servers are great for development. They run on local developer machine with fast iteration and no network latency. They are limited to local data sources, so configuration happens via JSON file. This is pretty perfect for prototyping and testing, but it's not ideal for production. Remote servers are what is ideal for production. And these are centralized deployments on cloud infrastructure like Azure Container Instances, AWS ECS, or Kubernetes clusters. Authentication is required for all collections. Remote servers support horizontal scaling for high throughput scenarios. If you have, let's say, 1,000 users, consider running 10 instances behind a load balancer. Autoscale can handle traffic spikes there as well. In practice, many production systems use hybrid architecture. Critical data requiring strong authentication goes through remote authenticated servers. Non-sensitive data like public documentation can go through local servers to reduce latency. This approach gives you fast access to public data and secure access to sensitive data. Now, error handling is pretty important as well. You should be implementing graceful degradation when servers are unavailable. If the GitHub server is down, your AI should still function with reduced capability. You should configure timeouts per server. So for example, in production, 5 to 30 seconds is a typical depending on the operation. You should also consider retry logic with exponential backoff for transient failures. If a request fails, let's say you should consider waiting 1 second and then retry. If it fails again, then you should wait 2 seconds, and then if it keeps failing, then you should keep waiting 4 seconds and 8 seconds. So essentially, this prevents overwhelming already existing server which might be down. Now, where it's possible, you should implement fallback to alternative data sources. If a primary database is slow, you should serve slightly stale data from the cache. Fallbacks keep your system functional when individual components fail. Now let's talk about integrating MCP with the existing AI workflows. First is the MCP plus RAG Hybrid Pattern. This works extremely well in the production. So MCP provides structural real-world data like user profiles or recent activity, whereas RAG provides historical context like documentation of past conversations. Combine both of them so that MCP can answer questions like what's happening now And RAG can answer questions like what's happened before. For example, in customer support, you should consider using MCP to fetch live ticket data from a ticketing system that gives you current status, assignments, and latest updates. Meanwhile, you should consider using RAG to search your knowledge base for similar issues and how they are resolved. Combining both of these will give you much better context than either just using one of them. Next is multi-server orchestration. In production, a single AI application typically connects to 5 to 15 MCP servers simultaneously. You might have a GitHub server, a Jira server, Slack server, PostgreSQL server, all connected at once. The language model decides which servers to query based on user intent. If the user asks about code, it queries GitHub. If they ask about tickets, then it queries the Jira server. You can make parallel requests to multiple servers to reduce latency. If a user asks, let's say, what are my action items for today, the language model simultaneously queries your email, your calendar, your Jira, and your Slack. These requests can happen in parallel. Just be careful not to overwhelm the language model with too much data at once. The next point is that the cost and performance optimization matters a lot. You should consider caching frequently accessed resources. Also consider setting your TTL based on data freshness requirements. User profiles might be, let's say, cached for 5 minutes, whereas real-time stock prices you should ideally use no cache at all or very minimal cache duration. Now, the next point is you should also consider using lazy loading. So, for example, only fetch resources when the language model explicitly requests them. Don't consider prefetching everything. If the protocol supports it, batch requests should execute where as possible. So, for example, you should monitor per server latency and fail fast on slow servers. If a server consistently exceeds the timeout thresholds, you should consider applying the circuit breaker pattern at least temporarily. Now, if you're considering migrating from custom integrations to MCP, here is the trust strategy. First, identify the existing custom connectors, Slack bots, GitHub API wrappers, database query helpers. Second, wrap that existing logic in an MCP server implementation. You don't have to rewrite everything from scratch. Third is you should consider doing gradual rollout. You should run MCP servers alongside the legacy integrations. Start with, let's say, 10% of traffic goes through MCP, monitor that carefully, and then increase to 50% and then 90% and then eventually 100%. Once MCP servers for your use case are proven to be working well according to your needs, only then deprecate the custom core integrations. This reduces the maintenance burden over time and gives you the safety of gradual migration where you can roll back if needed. Now, monitoring and observability are pretty important as well. You should be tracking server availability and response times. You should build dashboards which shows you which servers are up and how fast they're responding. You should be logging all the tool executions with user context. And you should also have alerting system based on, let's say, authentication failures or rate limit hits. You should also be measuring language model decision quality. Is it choosing the right, for example, server or tool for each request, or is it not? Also, you should be tracking user corrections to understand where the improvements are needed. Alright, so that was a complete deep dive into Model Context Protocol. We have covered the fundamentals and why MCP exists, the architecture with hosts, servers, and clients, the three concepts of resources, tools, and prompts. And it's also we covered in this video was the production patterns including security, deployment models, and error handling. After that, we covered integration with existing workflows using hybrid patterns and multi-server orchestration. And then we covered migration strategies. MCP is still pretty relatively new while the adoption is growing pretty quickly. So if you're building AI applications connecting to multiple data sources, MCP can significantly reduce your integration complexity. You should start simple with one or two servers, validate that they work well, and then only expand. Don't try to migrate everything at once. Thank you for watching today. If you have any questions, please let me know.